First, let me thank the organizers for setting up this conference and for Vladimir for kicking it off many years ago. I really wish I could be in attendance and must extend my apologies for not being able to make it. The work that I'll be presenting today is a collaborative project between myself and a number of my colleagues and students. This talk is about the variations in heat production through time and their geodynamic causes. Here I'm showing the granite heat production over the past 4 billion years. This record is derived from geochemical assays using XRF and ICP-MS techniques. I've collected none of this myself, only compiled them. What we find on this plot is that heat production increases throughout Archean-aged rocks. It then steps up at about 2 billion years, and at the same time a large heat production anomaly occurs in Australia, which seems to be largely constrained to the Mesoproterozoic. Globally, from 2 billion years to the present, there has been only minor variations in heat production. What caused these variations, particularly on a global scale? Well, I hope to convince you, or at least give you the inkling that during this talk, that it could be the result of geodynamic processes. We've examined in detail the changes in chemistry of granites and found that they mirror many of these changes, but do not completely explain them. It's also possible that the record of rocks that we have today are biased in some way by these same processes that have shaped the evolution of heat production. Let's look at a few of these processes and that can cause these variations in heat production. The processes listed here are all hypotheses for how each process would affect heat production. It is difficult to see how one could arrive at low heat production in the Archean as a result of any of these processes except thermal stability. For example, one would expect that mantle depletion to put most of the light ion lithophile elements, including all the heat-producing elements, into the crust early in Earth's evolution. This would deplete the mantle and lower the concentrations that can be added through time. In contrast, secular cooling would probably cause heat production to be low in the early Earth because melt fractions would be higher due to higher mantle temperatures. With time, cooling would cause a slow increase in heat production then with time. But none of these fit the pattern that we see in heat production. The hypothetical thermal stability curve is the only one that seems to fit our observations. So let's see if we can explore this a little bit more in detail and see if it makes any sense. Let's look at more than just granites. On the right, I show several groups of igneous rocks through time. All of these samples have been decay corrected back to their heat production at the time of formation, and then they've been binned and averaged. Uncertainties throughout this talk are shown as medians, with interquartile ranges, 25 to 75%. Each of the rock groups, regardless of how mafic or felsic they are, display similar patterns through time. They also show nearly consistent heat production over 4 billion years after being corrected for decay. It's almost as if there's a process that limits the amount of heat production. There's a nice correlation of heat production with the amount of SiO2 in a rock, and this allows us to adjust the heat production to an equivalent SiO2. It allows us to combine the analyses and increase the statistics and use smaller bin sizes in our analysis. The result on the left shows the decay and SiO2 corrected heat production as a function of age with the same nearly constant heat production through time. The result indicates that the heat production distribution of granites, regardless of when it was created, is the same. However, in the early Earth, there was more heat production in the mantle, so one would expect more heat production to be extracted by melting, since the process of granite formation wouldn't really have been any different in the past than in today. So why wouldn't heat production have been higher? Let's start from the premise that it was higher in the past and would decay to the present-day heat production regardless of its age. If this was true, then there is a deficit in heat production in the past relative to the present. Now let's explore what would happen to the geotherms in this case. If we compute a set of geotherms using the distribution of present-day heat production from rocks with crystallization dates from 0 to 200 million years, it doesn't matter what values we choose to use for the mantle heat flow because we're just comparing differences in heat production with all else being equal. This is a relative test, not an absolute one. In this case, granites are extracted from rocks when they reach about 720 degrees C. Plotting on the right, the depth at which this distribution of geotherms reach this threshold gives us an indication of the stability of the crust. When the depths are shallower, the crust is more likely to melt at the source, as the source rocks for granites are less common at deeper depths. Even if it doesn't melt, high temperatures at shallower depths will likely result in the reworking and metamorphism, possibly resetting high temperature geochronometers and making rocks appear younger than they are. Now let's add geotherms associated with Archean aged rocks and their present-day heat production distribution. The result is a set of cooler geotherms with the 75th percentile of Archean rocks matching almost exactly the 25th percentile of young rocks. The depths where the 720 degrees C isotherm is reached is much greater for most of the samples, so we would expect Archean crust to be more stable than young crust. Not a surprise. Now, looking at geotherms for those same Archean terrains using decay-corrected heat production, back to the original crystallization dates, we find a distribution of geotherms that is nearly the same as the present-day geotherms in young terrains. In fact, the median geotherms are almost exactly equal. The same goes for the depth to the 720 degrees C isotherm. Okay, now let's get a little crazy. Assume that the 0 to 200 million year rocks are actually Archean. What would their geotherms look like if they were decay corrected to the Archean ages? The result is a set of very hot geotherms. The distribution of these the depths to the 720 degrees C isotherms is now much shallower and no longer looks log normal or exponential or whatever, and looks more Gaussian instead. If the distribution of Archean rocks started with heat production distributions like D and ended with B, what would survive and what would be destroyed? The answer to that question can be difficult, but we can explore the possibility of survival if that were the case. Let's try an experiment here. To determine the survivability, we can take the ratio of the surviving distribution D to the original distribution B. This ratio results in the surviving distribution on the set of bottom plots. This distribution is reasonably well fit by a Gaussian cumulative distribution function. At this point, it is mostly a coincidence that the distributions behave this way, but it's sort of what you would expect to find. So to solidify this argument further, we really need to examine terrains that have been reworked, but not completely destroyed, and see if their heat production is systematically higher than intact Archean terrains. And if it is true that heat production has a significant impact on the ability of early crust to survive, or not, there are interesting questions about the composition of that crust and how thick it may have been. As radioactive decay decreased heat-producing elements, more and more of this crust may have survived, creating the appearance of a chemical evolution that didn't really occur. After all, the more recent models of crustal growth suggest that much of the continental crust formed very quickly and has just been recycled multiple times. Now let's turn our attention to the step in heat production at 2 billion years. To do so, we're going to look a little more closely around that period of time. We'll start with a data set of thermal gradients and metamorphic rocks, first compiled by Mike Brown and Tim Johnson. They've written a number of papers describing the database and tried to produce models for changes in the average thermal gradient through time. I think their models are basically meaningless. The database is very incomplete and it's heavily biased. I've been working with the database and nearly doubling its data set, but it's still very biased. There's an oversampling of very low thermal gradients. Turns out metamorphic petrologists really like rare rocks that have strange thermal histories. As a result, regional metamorphic terrains and especially low-grade rocks are poorly sampled. However, the sampling of very low thermal gradients resulting from subduction are very well sampled, and there are some clear gaps that are starting to come into focus. The most interesting of which is a large gap between 1800 and 1200 million years ago. There may be some other smaller gaps between about 2400 and 2200 million years and 900 and 700 million years. Some people have suggested that it may be a lack of preservation between these supercontinent cycles, but that doesn't make much sense to me because there aren't gaps associated with Gondwana or Pangaea, and Rodinia now appears to not have been a supercontinent, but one large continent and several smaller ones. So what exactly happened 2 billion years ago? It was the beginning of the assembly of Nuna, the first major supercontinent, at a time when there was nearly present-day volume of continental crust according to continental growth models. There are 2 or 3 orogenies responsible for Nuna, depending on how you count them. Nuna started forming around 2.1 billion years ago as a number of continental blocks assembled the core of the continent. As the interior orogeny was completing, a subduction girdle formed around the continent, bringing in additional exotic terrains, including the Watmay origin in northern Canada and bits of Proto-Antarctica and Proto-Australia, as well as the Congo. It also created new terrains on the margins of Laurentia and Baltica. This amalgamation created a very large continent that may have acted like a thick insulating blanket on the mantle. There's a growing body of work that demonstrates the insulating potential of continents, in particular supercontinents. Numerical studies such as this one by Lenardic et al. Show how 2 large pieces of continent merging can cause mantle temperatures to rise beneath the continent and fall beneath the oceans. Temperatures rise by as much as 150 degrees C in this simulation. And note that the temperature change starts to happen well before the continental bodies collide. On the right, geochemical estimates of mantle potential temperatures derived from Atlantic and Indian Ocean basalts suggest that when continents first started to break up in the mantle, beneath them it was quite hot. As the ocean basin enlarges, the time since breakup, the average temperatures start to fall. This data provides fairly reliable indirect evidence that continents have a significant insulating effect on the mantle and perhaps as much as 150 degrees C. Since the oceans created by the breakup of Nuna have all been destroyed, it is impossible to conduct a similar study of Nuna, but there are lots of igneous rocks that we can explore geochemically. To do so, we'll look at the Strontium-Yitrium ratio. The Strontium-Yitrium ratio is one of the best proxies for thermal gradients in the crust that we have today. It works because garnet really likes yttrium, but not so much strontium, and plagioclase really likes strontium, but not so much yttrium. The center plot shows a metamorphic pseudosection, a pressure-temperature plot, for a high alumina basalt. This is one of the source rocks for granitic melts, and I've included just a single field, or rather my co-author Renee Tamblyn has, that shows the garnet present to garnet absent field. Above the line, garnet is stable, and below the line, garnet will dissolve in the melt. Above the line, garnet retains the yttrium, causing the strontium over yttrium ratio to be high in the melt. Below the line, dissolving garnet contributes yttrium to the melt, causing a low strontium over yttrium ratio. The dashed lines in the background are lines of constant thermal gradients. Note that the garnet in, garnet out line is nearly parallel to the thermal gradient isoline. That means that this change in the thermal gradient, regardless of depth, will yield a similar change in the strontium-yttrium ratio. If only it were this simple, it might be possible to calibrate the thermal gradient in the crust to the strontium-yttrium ratio. Unfortunately for us, the world is far more complicated than that. So now let's add some more complications to the pseudosection, because not all granites are formed by the same starting material. Granites can be birthed by peelites, greywackies, samites, diorites, in addition to basalts, and I'm sure I've missed a few. Anyway, all of these rock types, the line defining the garnet stability in the residue, are nearly parallel to the thermal gradient isolines, as most temperatures associated with the formation of granites. As a result, the strontium over yttrium ratio generally tells us about the thermal gradient. High strontium over yttrium for low thermal gradients, and low strontium over yttrium for high thermal gradients. However, because of the very large range of thermal gradients associated with the wide range of compositions, it's basically impossible to calibrate the strontium over yttrium ratio to a thermal gradient other than in an average way. Numerical models of subduction may give us insight into the process of formation and exhumation and preservation of low thermal gradient terrains such as blue schists and cold eclogites. Under normal conditions, or at least what we think of normal today, the subducting oceanic plate, shown on the upper left panel, descends into the cool upper mantle. As a result, the oceanic plate is rigid and can descend to great depths. Under hotter mantle, like those found in the early Earth and in the lower right panel, the slab would have been weak, and this weakness can cause the slab to break off before reaching the depths needed to form UHP metamorphic rocks, or would carry them into the mantle when it did break off, preventing them from being exhumed and preserved. What's the strontium-yttrium ratio through time tell us? The strontium-yttrium ratio, shown in the top time series, has a very large drop at about 2 billion years, suggesting a rapid increase in the thermal gradient as Nuna is forming. The ratio continues to fall for another 400 million years before it starts to recover. Many heavy rare earth elements behave in a similar manner as yttrium, and it's good to see that the strontium over heavy rare earth ratio is nearly identical in behavior. The gadolinium yttrium ratio is also a test that we can use, and it's a test of amphibole, which has a reservoir of gadolinium, but could also be responsible for the strontium yttrium ratio. But it shows a relatively similar behavior, suggesting that the thermal gradients would have indeed increased. Now in the rightmost plot, based on the strontium yttrium pattern, we interpret the variation of thermal gradient something like the one imagined here in red. There is a temperature threshold for which slabs are stable. When the thermal gradient falls below this threshold, cold eclogites and blue schists may form. When the thermal gradient is above this, ultra-high pressure rocks are not preserved in the rock record. While the gaps may have happened more than once, it seems clear that by 2.2 billion years, the Earth was starting to preserve cold eclogites, and by 1.7 billion years, the insolation of Nuna raised thermal gradients sufficient to stop the preservation of these unique rocks. By 1.2 billion years, the thermal gradients had fallen enough to preserve them again. Whether this process happened in response to Rodinia is not yet clear. Pangaea and Gondwana clearly lack these gaps, suggesting that the thermal gradients may have decreased again during the intervening period sufficiently that any insulating effect of supercontinents is not enough to stop the preservation of cold eclogites and blue schists. The changes seen in strontium over yttrium are seen in nearly all trace elements, including uranium and thorium, though not in potassium. It stands to reason that this insulation effect is responsible for the step in heat production at 2 billion years. While I wouldn't call our results definitive yet, there are certainly tantalizing clues that the thermal stability was responsible for the bias and preservation of low heat producing Archean terrains and possibly bulk compositions of Archean crust. I think Paul Morgan had this idea right back in 1985, which sadly has seen very little appreciation in the literature or discussion among petrologists. Our last major point is that the thermal insulation associated with Nuna had a profound impact on the Earth's trace element chemistry, including heat-producing elements. In the case of thermal stability, geodynamic processes may have been significantly influenced by heat production, and with supercontinent insulation, geodynamics may have had a significant impact on heat production. In both cases, these processes from the Archean influence the thermal regime of the continental lithosphere and its evolution today. I would like to thank everyone for watching this presentation. I sincerely wish that I could be there with all of you. You're my favorite community of geoscientists, and I'd especially like to extend my thanks to David Chapman, who I know is in attendance, and for inspiring me in my journey as a scientist. If anyone has any questions or interest in collaborating on similar types of adventures, please get in touch with me by email. Thank you.